Hi, everybody. This is Professor Monty. Today we are going to look into section 1.6, the product and the quotient rules. So remember, a product means we're multiplying two things together, and a quotient means we're dividing two things. But the big question is, why do we need these? So let's kind of sketch that down. Why do we need the product and quotient rules? That's not a very good E, is it? Let's make that a little nicer. So why do we need the product and quotient rules? Well, let's look at an example. Say I've got a function, we'll call it f of x, and say it's x squared times x to the third. We know by properties of exponents, we would just add those exponents together. So that's really x to the fifth power. Well, we know from there that if we take the derivative of that, we just use the power rule, bring down the 5, we get 5x, lower the exponent by 1. We know 5x to the fourth should be the right answer. But can't we do the same thing we did with addition and subtraction, where if we're either adding or subtracting two functions, we just take the derivative of each one of those individually and then add or subtract as appropriate? Can't just take the derivative of each of those products? Answer. Well, let's check. So we've got the same function here, but what I'm going to do is we're going to check if we can take the derivative of each of those and then multiply them together. So the question would be, is the derivative of a product of the two derivatives? So if I do that, and we've got this x squared, let's erase that real quickly because I don't know what the heck is going on there. So if I've got this x to the third, is the derivative, we'll put a big question mark here, is f prime of x just the derivative of x squared times the derivative of x cubed? Well, let's see. The derivative of x squared we know is 2x to the first, or just 2x. The derivative of x to the third is 3x squared. And when we multiply that, we get 6x to the third power, which clearly is not 5x to the fourth, which we know the right answer is. So clearly, that's a big no. So I can't just multiply the product of the derivatives to get a right answer. Let's show the same is true for the quotient. So let's try this. Consider, let's say we've got a function this time, and we'll make it, say, x to the seventh over x to the fourth. Remember properties of exponents. This time we subtract the exponents. We get x to the third. And so that's easy. I know the derivative of that is just 3x squared. So we know that's true. Well, let's check. And we'll actually write this time quotient of derivatives. So if I go f of x equals x to the seventh over x to the fourth, and then I take the derivative of the numerator, 7x to the sixth, and the denominator, 4x cubed. Well, the 7 and the 4 are relatively prime. They don't reduce. So I get the 7/4, and then I subtract the exponents, so I get x to the third. That clearly is not 3x squared. So that doesn't work either. I'm just going to put a no. I didn't really answer a question, but we'll say, no, I can't do that. Well, let me show you the product rule and the quotient rule. And we'll do them one at a time. So we'll do the product rule first. I will show you that. And then we'll do the quotient rule and show that we're actually going to get the right numbers. All right. So let's see. And what did we choose for the product rule? We were doing x squared times x to the third. So we'll do that as our first example to make sure this product rule thing really works. So here is the product rule. Here's how we actually have to take the derivative of a product. Now the book writes it, it doesn't look very simple when you read it, but the idea is this. Say we've got some capital F of x, which is little f of x times g of x. So my initial function is a product. Well, when we take that derivative, here's the product rule. Now I'll show you how they write it, which I'm not a huge fan of. And then I'll write it the way I like to think of it. They're going to say, okay, it's this first function times the derivative of the second function. They're going to put a bracket there instead of a parenthesis, so we don't have a double parentheses there. So it's the first function times the derivative of the second plus the second function times the derivative of the first function. Now that looks just ridiculous to me. So the way I like to write it, f prime of x is the first times the derivative of the second plus the second times the derivative of the first. So that to me is a lot simpler. I even write it simpler than that, actually. Now, the notation's not good, but we're not mathematicians here. If you're a mathematician, you're in the wrong class. So it's the first times the derivative of the second plus the second times the derivative of the first. That's how I like to think about it. And notice we've got multiplication and addition going on. So you may see another author or a friend in another class or even yourself. You don't do it in this order, but notice each time it's one of the functions times the derivative of the other. Multiplication doesn't matter, so it doesn't matter the order that you do it. And addition's commutative as well, so it doesn't matter which you do first. But it's one of the functions times the derivative of the other, plus, and then you just switch the one you take the derivative of. So it's a nice, easy thing. But let's try that on that x squared times x to the third to make sure that it does work. So let's recall, we already said that if I have, and we'll call it capital F of x so that we don't get the small f and g confused. So if my original function was that x squared times x to the third, oops, might as well write it in the same order we had it before, x squared times x to the third, which we knew was x to the fifth, which we knew the derivative of that was 5x squared, 5x to the fourth rather. Okay, let's try this product rule. All right, so remember, the product rule, when I go f prime of x, it's the first times the derivative of the second plus the second times the derivative of the first. Well, in this case, there's f and there's g. F is x squared, g is x to the third. So the first is just x squared times the derivative of the second. Well, the derivative of x to the third is 3x squared plus g, which was x to the third, times f prime. Well, the derivative of f, since f was x squared, is just 2x. Now, when I multiply these out, remember I'm adding the exponent, so I get 3x to the fourth plus the x to the third times x. I add those, I get an x to the fourth again, plus 2x to the fourth. These are like terms, so I can combine them by adding the coefficients, and I get 5x to the fourth, which, that does check from above. We know that should be the derivative, and in fact, it does work. So it's crazy little formula. Doesn't seem like it should work, but in fact it does. Now, I haven't proven it. I've just shown an example of one of them working. If this was a science calculus class, we may care about the proof. I don't care about the proof. I just want it to work, and it does. So that's my product rule. So there's one. Let me show you a couple more examples of this, then we'll go on to the quotient rule. Then we'll do a couple applications. All right. So I'm in the book, and let's go to problem 4 out of the textbook. It gives us g of x is equal to 3x minus 2 times 4x plus 1. All right. Now, granted, if we wanted to, we could FOIL that out, and then we've just got a nice trinomial once we combine like terms that we could take the derivative to. And in fact, let's do that to make sure that when we do the product rule, we get the right answer. So let's FOIL this out. So let's see, 3x times 4x is 12x squared. 12x squared plus 3x minus 8x minus 2, combine like terms, 12x squared minus 5x minus 2. So that's my function g of x. And if I take the derivative of that, now I'm just using the power rule and the addition subtraction rule, 24x minus 5. I know that's the right answer. I haven't done the product rule, but we will. All right, let's try the product rule. So we'll say using product rule. Now I will tell you, the product rule is more complicated to use. So if you can just multiply out the problem originally to a nice simple polynomial and then take the derivative, that's easier to do. We will see times where we can't multiply it out first. That's why we have to learn the rule, but we learn it with some simple things first. Okay, so let's say using the product rule. So remember, so g prime of x. Now, don't get too confused, because up here, this 3x minus 2, that's going to be my f, and the 6x plus 1 is going to. So we've already got another g prime of x here, so try not to get confused that we're referring to that 4x plus 1 as g and taking its derivative for g prime. So let's see. So we'll go through it, and then I'll write above it what we were actually doing, maybe below it. We'll see. So let's see. We've got the first 3x minus 2, 3x minus 2, times the derivative of the second, that's just 4, plus the second times the derivative of the first, it's just 3. So this piece was, I don't want to write it that way, let's write it this way. This was the first times the derivative of the second, plus the second times the derivative of the first. So I just used the product rule. Now we can multiply out and simplify things, combine like terms. So let's see. So we get 12x, let's move that up a little bit, minus 8 plus 12x plus 3. And if I add the 12x's together, I get 24x. Negative 8 plus 3 is minus 5. And once again, check, that was what my answer was supposed to be. So the product rule did work nicely. And we see how that works. Again, we'll get to problems that we cannot multiply out first, but not yet. All right, let's do one more example of this just to make sure that we kind of have it. Now this one we could multiply out first, but it's a little bit uglier because it's not polynomial. It's 4 times the square root of x plus 3, and then times x cubed. Now, remember that 4 times the square root of x is really 4x to the 1/2 power plus 3. Not a very good 3, is it? And then times x cubed. We could multiply those, add fraction, add the 1/2 to the 3 to get the denominator, but we're just going to leave it this way so that we can take the derivative. And so now when I do y prime, and if you want to call that dy dx, you can. We'll just call it y prime. We get the first times the derivative of the second plus the second times the derivative of the first. Well, the 1/2 times 4 is 2, and then x 1/2 minus 1, negative 1/2. And then that plus 3 is just a 0. So here's what I had. This was f, this was g, and then down here I did f times g prime plus g times f prime. Now I will simplify this as far as I can. So let's distribute in here, multiply these two together, and we'll combine any like terms we have. Oops. I don't want that to be blue anymore. Let's go back to black. So I get y prime is equal to, let's see, the 4 times the 3 is 12. Now I'm adding the exponents. I've got the 1/2 plus 2, but I'm multiplying that by 2 over 2 to get a common denominator. So that's 4 halves. So when I add together, it's 5 halves. So it's 12x to the 5 halves. And then plus 9x squared. And I multiply over here. Now I have 3 minus a half, which is 2.5. And again, 2.5 is 5 halves. So plus 2x to the 5 halves. And now these two I can add together. And I get y prime equals 14x to the 5 halves plus 9x squared. And there's my derivative. This one we haven't checked with anything, but that's okay. Oftentimes we won't have anything to check with, but that's our answer. So anyway, there's some examples of using the product rule. Those are actually the only examples I'm going to do today of the product rule. Hopefully that was enough, but you can go back and practice. You can look over those. Again, a lot of times a good thing to do is just look at the first line when I write the problem and then see if, pause the tape and see if on a piece of paper you can go through and complete the derivative on your own and then check the tape and make sure you have the right answer. And if not, just see where you might have got stuck. Okay, so let's go back to the quotient rule. The quotient rule looks a little bit uglier and we have to be a little more careful. So the quotient rule, now I write it differently than the book does because I've got a little saying that a student in previous years taught me to help me remember the rule. But say I've got a quotient, we'll call it Q of X to imply it's a quotient. And then what I'm going to do, a lot of authors will use D of X on the top, N of X on the top for the numerator and D of X on the bottom for the denominator, but that doesn't work with the rhyme that I have. What I have is the high and the low. So if my quotient rule is high over low, I've got something like this. It's a quotient. We've got some division. But then the derivative of that quotient, again, I'm going to drop the x's just to make it look better, is low d high, so the derivative of the high, low d high minus high d low, square the bottom, and away we go. So here's my little saying. As silly as it sounds, it helps you remember. It's low d high, d being the derivative, minus high d low, square the bottom, and away we go. So now you have to say away we go because it rhymes with high D low. So that gets us in the right order. Since we have a minus here instead of a plus, the order matters. You have to start with the low D high. So low D high minus high D low, square the bottom, and away we go. Now that bottom that's squared, it's just squared. It's not the derivative or anything, it's just the bottom. Whatever the denominator was, you're just going to square it. And you don't have to multiply it out. You want to leave it just as that quantity squared. So I'll show you as we do a couple of those. but I think that'll help real well. Students typically like that little saying because it makes sense to them. I mean, maybe it doesn't make sense why we do it, but it is definitely pretty easy to remember. So low D high minus high D low, square the bottom, and away we go. All right, so that, and I'll box it here, that's my quotient rule. And let's try one of these. So let's think. What we had before was x to the 7th over x to the 4th. And again, we knew that we subtracted exponents, we get x to the 3rd, and I know the derivative of that has to be 3x squared. All right, so I know that's true. Let's apply the quotient rule to make sure it works. So we'll say using quotient rule. All right, so here we go. So the derivative is. Now, I like that saying a lot better than the way we learned it when I was in school. It was just the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared, which is fine. I still remember it these several years later, but it doesn't rhyme. So we've got f prime of x, so it's the bottom, so it's low d high. So low, well, that's x to the 4th. D high is the derivative of the numerator, 7x to the 6th. So low d high minus high, x to the 7th, times the derivative of low, d low, 4x cubed. Square the bottom, and away we go. So here's what I did. It's low d high minus high d low, and then square the bottom. That's all it is. We don't have to make it too difficult, too crazy. This one, of course, easy because it's just monomials, but once you understand the quotient rule, even if the values are harder and you have higher polynomials or even not a polynomial on the top or the bottom, it doesn't matter. It just makes the algebra a little bit harder, but it's the same procedure. So let's combine some things here. Clean this up. So the x to the 4th and the x to the 6th, remember I add the exponents, so that's going to be 7x to the 10th. And then minus 4x to the 10th again. And then on the bottom, remember power, we multiply exponents, so that's x to the 8th. Because that'd be an x to the 4th times an x to the 4th. So we just get 8 of them there. All right, so we're almost done. So keep cleaning. So the 7 minus 4, those are like terms. We can add those together. They're both x to the 10th. So I get 3x to the 10th. Let's write f prime of x. 3x to the 10th over x to the 8th. And now I subtract the exponents. The 10 minus 8 is 2. I get 3x squared. And notice, check. It's exactly what I had there. So this crazy rule, even though it looks insane, actually works. All right, so there's the quotient rule. We'll do a few more of those, kind of get our feet under us a little bit there. But let's see. So that one we had just made up from the problem previously. I'm going to jump into problem 46. They give us little f of x is equal to, the numerator is 3x squared minus 5x. The denominator is x squared minus 1. Now notice this is a problem I can't simplify. So the quotient rule is easy to get a problem that doesn't simplify first. The product rule, remember any of the 3 problems we did of product rule problems, we could have simplified, multiplied out first, and then just taken a straight derivative using the power rule. But this can't simplify. There's nothing I can do here to simplify this. So I want to take the derivative, but I'm going to use the quotient rule. So f prime of x, low d high, so that's 6x minus 5, there's low d high, minus high d low 2x. Square the bottom and away we go. So that piece right there, that's the quotient rule. That wasn't hard. None of that was difficult to do. We just have to remember the order. So again, low d high minus high d low, square the bottom and away we go. And so of course this was the high and this was the low. But that's what I did. Now I'm going to multiply out, I'm going to simplify, see how simplified I can get it. A lot of these don't simplify real nicely, but I'm going to FOIL this piece out. Here I don't FOIL. We have to be careful because I'm distributing this minus also, but let's see what we've got going on there. So let's see, so I've got my f prime of x. So x squared times 6x is 6x to the third. I'm actually going to do the 5 times the x squared this time, the x squared times the minus 5. Well, I guess that's the next thing we see anyway. So minus 5x squared. I just wanted to keep it in powers, descending powers of x, but this is going to work well anyway. Minus 6x plus 5. That's my first piece. Now, I've got this 2x here, and I've got the minus here. So I'm going to think I'm distributing a minus 2x. So a negative 2x times the 3x squared is going to be negative 6x to the third. And the minus 2x times the minus 5x is going to be plus 10x squared. All over the bottom squared. Remember, I'm not going to actually square the bottom. I don't need to FOIL that or anything. What we're going to do later, we're going to be setting derivatives equal to 0. I want to know that in its factored form, because then I can set it equal to 0. It'll tell me when the fraction's undefined. That will be useful for me. Or if I'm going to reduce the fraction, it has to be factored first. It's already factored, so I don't want to mess with the denominator, except maybe to reduce. All right, so anyway, let's look what's going on in the numerator. This x to the third cancels the minus 6x to the third. This minus 5x squared and the plus 10x squared go together. They're like terms. They have the same exponent. That's all I can simplify. So let's go one more level here. So the minus 5x squared plus 10x squared is plus 5x squared. And then I still have the minus 6x plus 5. That's the end of the numerator. And on the bottom, it's just x squared minus 1 squared. And that is my derivative. We could look to see if the top factors, but I know I can't cancel an x squared minus 1. That's not going to be one of the factors. So whether it factors or not is irrelevant at this point. That's as simplified as it can get. Factoring, not reducing, doesn't make it simpler. And some instructors will even say, no, I don't want things factored out that if I'm not setting it equal to 0 and solving. So that's my quotient rule. And we'll see a couple more examples of it as we do the 2 applications. Okay, so we'll get a little more practice with that. But what I want to do here, I've got a couple applications that I took out of the book. I think one of them is ready to go here. Here it is. It's problem 53. It says average cost. Preston's Leatherworks finds that the cost in dollars of producing X belts is given by C of X equals 750 plus 34X minus 0.068X squared. Find the rate at which average cost is changing when 175 belts have been produced. Now, they're talking about something here. They're talking about, well, we'll go up to the original problem. Average cost. We haven't talked about average cost yet. Let's kind of sketch this off to the side. Now, we've got, for instance, total cost. That would be C of X. That's if we want to say, hey, what's the total cost for 100 units? We'd plug in 100 for X, we'd plug it in to our cost function, and we'd get the cost of all 100 of those units. But if we wanted to know what they cost on average, the average cost, it's just like any other average. if we want our exam average, we'd add up all the exams and get our total exam score, similar to total cost. Let's make that an equals. So we're going to get the total value, total cost, and we divide by the number. Well, the number, let's say, I don't want that symbol there. I want to say number of units. So we'll say number of units. That's how we're going to find the average. So if it's, for instance, $400 and there's 100 units, 400 divided by 100 will be $4 per unit. And that would be my average cost. So this formula, now the formula to do this for average cost, they're going to put a bar over the top of the cost function over the C to say, hey, it's not total cost, it's average cost. We use that symbol in statistics. When we know the average of the x's, we just call it x bar. We put a bar over the top of the x, and that means the average of the x's. Well, that's the average of the cost. Well, it's total cost, which is C of x, divided by number of units, which is x. So here's a new formula we haven't had before. But that's how we find average cost, just total divided by the number. And notice, look, it's a quotient. Hence, that's why we're in the section for the quotient rule. Now, I will say over here, similarly, yeah, it looks like similarly, if I do R bar of X, that's R of X divided by X, that's average revenue. And if I do P bar of X, that's P of X divided by X. So that's profit divided by number of units is average profit. So that's average profit. All right, and let me box these together so we know which goes with which. So there's average profit, and there's average revenue. And then, of course, we already have the average cost. So I was talking about average cost, so we'll go ahead and we'll go through and we'll do this. Find the rate. Now, here's a big key for you. Whenever they say the rate at which something is changing, that always means the derivative. That's what the derivative is. Remember, it's the rate of change. Oops. So when we want to find the rate that something's changing, we take the derivative. That's what the derivative represents. Okay, so find the rate, or the rate average cost is changing, or the derivative, in this case, of average cost. Here, I'm not going to write average cost. I'm going to write of C bar of X. When 175 belts have been processed. Well, here, let's in fact clean that up a little bit. We'll say this. I'm not cleaning that up yet at all. So it's the derivative of C bar of X, but in fact, what we're trying to find is C bar prime, the derivative of average cost. Oops, I wasn't going to write the X, at 175 belts. That's what I'm trying to find. The rate of change, or the derivative of average cost when we're at 175 belts. Okay, so here's what we do. We start off, we've got the function. So we say, okay, I need to find C bar of X. Well, I know that's C of X divided by X. Well, that's 750 plus 34X minus 0.068X squared, all divided by X. Now, again, this is one of those, I can simplify first if I want to. I can divide each piece by X, and the 750 divided by X is 750X to the negative 1. The 34X over X, the X's cancel, etc. And I can get 0.0 0.068x to the first power once I reduce, and then take the derivative. But we'll use the quotient rule to get a little more practice with that. Okay, so C bar prime of x, low, d high, well, the 750 is a constant, it goes to 0. The 34x, the x goes away, minus, and then just to make sure that I don't make any silly calculation errors, I'll put in 0.068 times 2, and I get 0.136, so minus 0.136x, so that's low d high minus high, the whole thing, whole numerator, d low, the derivative of the bottom is just 1. Square the bottom, and away we go. So again, let's see what we did. So this was high, this was low, and I did low d high minus high d low. Square the bottom, or square the low, and away we go. I guess we could say square the low and away we go. That rhymes too. But then it didn't have to have the high d low to rhyme, and then we might make a mistake. So we're just leaving it as the bottom squared. Okay, so we've got all that. Now let's just clean it up. C bar prime of x. I'm going to distribute here, so I get 34x minus 0.13x squared. The 1 times negative, I'm just distributing negative 1. So minus 750 minus 34x plus 0.068x squared all over x squared. Again, this simplifies nicely. This 34x cancels the minus 34x. These two x squareds are like terms, so I can add them together, and I'm getting it negative 0.068x squared. C bar prime of x, let's see, negative 0.068x squared minus 750. That top simplified quite nicely, all over x squared. There's the derivative of the average cost. And remember, they said find they literally said find the rate of change of average cost at 175 belts. Do I have that number right? 175 belts. So I'm going to take that and I'm going to find C bar prime of 175. So I plug in 175 wherever I have an X. Make sure you hit equals after the numerator before you divide by the denominator because of that subtraction up there. So I'm doing this in my calculator. I just hit equal. But if I don't do that, it's going to divide by the 175 squared before it does the subtraction. I don't want that to happen. So I go negative 0.068 times 175 squared minus 750 equals divided by 175 squared. And I get negative 0.0925. Negative 0.0925. That's a really small number. But let's talk about what it means. It's the rate of change of average cost. So that's cost per belt. And this is in dollars per belt. And so what they're saying is for each individual belt, the average change is that the cost per belt is going down a little bit over 9 cents when I make one more unit. Which unit are we talking about? Well, right now we're at 175 units. Remember, this is the instantaneous rate of change at 175. So if I make one more belt 176, the average cost per belt for all 175 of those previous belts is going to go down about 9.25 cents per belt. So that would be my interpretation. It would be something like, if we increase production, now it's by one, but it's specifically for the one belt to get to 176. From 175 to 176 belts. And it's specifically here because if I plug in, say, 200, I'm going to get a different answer. That would be increasing from belt 200 to 201. But if we increase production from 175 to 176 belts, average cost per belt will decrease, because it's a negative, by, and we'll make it, we could do a dollar sign this way. If we didn't want that much of a decimal, we could call it 9.25 cents per belt. Oops, if we wanted to. I don't like that belt there. Why? Per belt. So either way we say it, in dollars, it's 0.09 and 9.25 cents per belt. But that's what that value means. So that's an example of a quotient rule where we've actually applied it to figure something out. All right, let's do one more problem and we'll call it a day. So let's look at this one. Under the situation, I thought this problem was nice and appropriate. It's problem 62, but let me go grab it. Let's see, where's my 62? There it is. We'll copy that. Go back in. Paste it right there. Temperature during an illness. How about that? Gina's temperature T during a recent illness is given by, and they give us the function, where capital T is the temperature in degrees Fahrenheit and T little t in hours. And notice it goes up really quickly and spikes, and then it starts to come down much slower than it went up. And they ask us a bunch of questions. Find the rate of change. What in the world is rate of change? Hopefully you're saying, well, that just means the derivative. And you would be absolutely right. So remember, the rate of change means the derivative. So find the derivative or the rate of change of Gina's temperature with respect to time. So we're finding the derivative. Now with respect to time, it's the change, D, the change in capital T, the temperature, with respect to little t time. It's d capital T dt. That would be Leibniz notation, or we could just write it in Newton's notation as T prime of T. And then find Gina's temperature at time T equals 2. We'll look at that in just a second, but let's go step by step here. So I'm going to erase this stuff so it doesn't get in our way as I do the problem. So I want to be able to see the problem. So we're going from right there where the temperature is. So part A, find the rate of change of temperature. Okay, so we want T prime of T. Well, definitely a quotient rule problem, so I do low T squared plus 1 d high times 4 minus high for T d low 2T. Square the bottom and away we go. T squared plus 1 squared. Now I've got that plus 98.6. That's a constant, so the derivative is just 0. Well, let's clean this up. So again, if you want to see what I did, we did, let's see, low d high minus high d low, square the bottom, and away we go. So I'll multiply those out. I've got T prime of T equals 4T squared plus 4 minus 8T squared, all over T squared plus 1 squared. Well, the 4t squared minus 8t squared is minus 4t squared plus 4. So that's fully simplified. So what I just did right there is I combined these two to get this piece, in case you're curious. Okay. So there's my derivative. I'm just going to box that whole thing. Now I'm going to erase that green circle here so that we can just see that as a derivative. Okay. Now B says find Gina's temperature at T equals 2. Well, her temperature at any given time is the original function. That's T of 2. That's her temperature at time 2. So we go back to the original function, plug that in. So we get 4 times 2 over 2 squared plus 1, and then plus 98.6. All right, let's see what I get. Well, notice it's just, I'm just going to plug it in as 8 divided by 5 plus 98.6. And I get 100.2. And that's in degrees Fahrenheit. It's not a very good circle, is it? So after 2 hours, her temperature is a little bit over 100 degrees, 100.2. Notice it's almost hit the peak because the peak's a little over 100.5. Part C says, find the rate of change of Gina's temperature at T equals 2. Well, the rate of change is the derivative. So that's T prime of 2. So now I go into the derivative and plug that in. So negative 4 times 2 squared plus 4 over 2 squared plus 1 squared. Again, remember, top has to be all one piece before you do that division. So I get negative 4 times 2 squared plus 4. So the numerator is negative 12 divided by, and that's going to be 25. But we can plug that on, it's negative 0.48. So what that tells me is it's negative, so her temperature is now going down. How much? Well, it's going down about 0.48 or almost 0.5, almost half a degree per hour. So that's what that is. The interpretation is that temperature is dropping by 0.48 degrees Fahrenheit per hour. That's how quickly it's dropping right now. So she's getting better. Her temperature's coming down anyway. So that's a plus. But do understand what that means. Getting the value negative 0.48, if you don't know what it means, like, oh, I got the number. Hey, I'm great. Well, what does it mean? Oh, I don't care. That's not very helpful. All right. So next step, and these are going to follow just from what we did, but it's just to see how things are changing. So we were at 2. So graphically, if we were at 2, what we're doing is we're coming up here and we're a little bit over here past the peak. I know we're past the peak because the derivative was negative, the temperature going down. So the graph must be going down at that point. Now we say, well, let's look at the end of one day. So we're going at 24 hours. Well, notice her temperature is going to be a lot lower, but it's going down a lot slower because it's not as steep. So D says, what's her temperature after day 1? Well, that's her temperature after 24 hours. So I go back again to the original function and I go 4 times 24 divided by 24 squared plus 1 and then plus 98.6. Let's see, 4 times 24 equals divided by parentheses for the bottom, 24 squared plus 1. Make sure you have the parentheses on the bottom or else you're only going to divide by the 24 squared and then add 1 to the total. and then plus 98.6. 98 point, if I go to one decimal, it's 98.76, so it'd be 98.8. So it's almost back to normal degrees Fahrenheit. How quickly is it changing? Find the rate of change. Well, again, that's the derivative, so we'll plug that in. T prime of 24, negative 4 times 24 squared plus 4 divided by 24 squared plus 1 squared. I think I plugged that all in right. Let's look at the derivative. Negative 4t squared plus 4 over t squared plus 1 squared. There we go. Again, bracket. Negative 4 times 24 squared plus 4 equals negative 2,300, but then divided by parentheses, 24 squared plus 1, close parentheses, squared, equals negative 0.006908 stuff. This would reduce to negative 0.007. So the temperature is still going down, but really slowly. Degrees Fahrenheit per hour. It's a rate, so that's why it's not just in degrees Fahrenheit, but it's a rate. It's the change in Fahrenheit over the change in hours. Remember, it's a slope. It comes from this idea, the change in Fahrenheit over the change in hours, or the change in time, if you will. They actually did this one as temperature over the change in time, but that's what we're talking about there. Now, it's not literally the change in temperature over the change in time because it's the rate. We had to take the limit as h goes to 0. But at that point, that's the rate of change. Okay, that is the end of this section. Notice you had to know your shortcut properties really well to do the product rule and the quotient rule. So I went through those pretty quickly, but practice these. We're going to be using them essentially for the rest of the semester. You will see the product rule and the quotient rule come up the rest of this chapter, the rest of the next chapter, and the rest of the next chapter. So you'll see it in chapter 1, you'll see it in chapter 2, you'll see it in chapter 3. All right, so good luck with that. Don't get discouraged if it seems hard, if it seems easy, keep going. If it seems a little difficult, just put in the time. You need to pass the class, and you can. Everybody can pass this if they just put in the appropriate amount of effort. Okay, well, best of luck. I will see you all back in the live session.